So this cell, just the entire RNN, I'm only visualizing one part of the hidden state, basically. There's many other hidden cells that evolved in different ways, and they're all evolving in different times, and they're all doing different things inside the RNN hidden state. Good?
Is it still single layer, or have you increased the depth to get like more complex cells?
We'll go into, are you asking about multi-layer RNNs and so on? We'll go into that in a bit. This is, I think, multi-layer RNN, but you can get similar results with one layer. Good?
How are you defining a cell turning on?
Yes, so these hidden cells were always between -1 and 1. They're an output of a 10H. And this is from an LSTM, which we haven't covered yet. But the firing of these cells is between -1 and 1, so that's the scale that sets this picture. OK, cool. OK. So RNNs are pretty cool, and you can actually train these sequence models over time. About roughly 1 year ago, several people have kind of realized that you can actually use this in a very neat application in the context of computer vision to perform image captioning. So in this context, we're taking a single image, and we'd like to describe it with a sequence of words. And these RNNs are very good at understanding how sequences develop over time. So in this particular model that I'm going to describe, this is actually work from roughly a year ago. Happens to be my paper. I have pictures from my paper, so I'm going to use those. So we're feeding an image into a convolutional neural network. And then you'll see that this full model is actually just made up of 2 modules. There's the convnet that is doing the processing of the image, and there's the recurrent net, which is very good with modeling sequences. And so if you remember my analogy from the very beginning of the course, where this is kind of like playing with Lego blocks, we're going to take those 2 modules and stick them together. That corresponds to the arrow in between. And so what we're doing effectively here is we're conditioning this RNN generative model. We're not just telling it sample text at random, but we're conditioning that generative process by the output of the convolutional network. And I'll show you exactly how that looks like. So suppose I'm going to show you what the forward pass of the neural net is. So suppose we have a test image, and we're trying to describe it with a sequence of words. So the way this model would process the image is as follows. We take that image, and we plug it into a convolutional neural network. In this case, this is a VGG net. So we go through a whole bunch of conv, max bool, and so on until we arrive at the end. Normally, at the end, we have this softmax classifier, which is giving you a probability distribution over, say, 1,000 categories of ImageNet. In this case, we're going to actually get rid of that classifier. And instead, we're going to redirect the representation at the top of the convolutional network into the recurrent neural network. So we begin the generation of the RNN with a special start vector. So the input to this RNN was, I think, 300-dimensional. And this is a special 300-dimensional vector that we always plug in at the first iteration. It tells the RNN that this is the beginning of the sequence. And then we're going to perform the recurrence formula that I've shown you before for a vanilla recurrent neural network. So normally, we compute this recurrence, which we've saw already, where we compute wxh times x plus whh times h. And now we want to additionally condition this recurrent neural network not only on the current input and the current hidden state, which we initialize with 0, so that term goes away at the first time step, but we additionally condition just by adding wih times v. And so this v is the top of the convnet here. And we basically have this added interaction and this added weight matrix w, which tells us how this image information merges into the very first time step of the recurrent neural network. Now, there are many ways to actually play with this recurrence and many ways to actually plug in the image into the RNN. And this is only one of them, and one of the simpler ones, perhaps. And at the very first time step here, this y0 vector is the distribution over the first word in a sequence. So the way this works, you might imagine, for example, is you can see that these straw textures in a man's hat can be recognized by the convolutional network as straw-like stuff. And then through this interaction wih, it might condition the hidden state to go into a particular state where the probability of the word straw could be slightly higher. Right? So you might imagine that the straw-like textures can influence the probability of straw, so one of the numbers inside y0 to be higher because there are straw textures in there. And so the RNN from now on has to kind of juggle 2 tasks. It has to predict the next word in the sequence in this case, and it has to remember the image information. So we sample from that softmax. And suppose that the most likely word that we sampled from that distribution was indeed the word straw. We would take straw, and we would try to plug it into the recurrent neural network on the bottom again. And so in this case, I think we were using word-level embeddings. So the straw word is associated with a 300-dimensional vector, which we're going to learn. We're going to learn a 300-dimensional representation for every single unique word in the vocabulary. And we plug in those 300 numbers into the RNN and forward it again to get a distribution over the second word in the sequence inside y1. So we get all these probabilities. We sample from it again. Suppose that the word hat is likely now. We take hat's 300-dimensional representation, plug it in, and get the distribution over there. And then we sample again. And we sample until we sample a special end token, which is really the period at the end of the sentence. And that tells us that the RNN is now done generating, and at this point the RNN would have described this image as a straw hat period. Okay? So the number of dimensions in this y vector is the number of words in your vocabulary plus 1 for the special end token. And we are always feeding in these 300-dimensional vectors that correspond to different words and a special start token. And then we always just backpropagate through the whole thing at a single time. So you initialize this at random, or you can initialize your VGGNet with pre-trained from ImageNet. And then the recurrent neural networks tell you the distributions, and then you encode the gradient, and then you backprop through the whole thing as a single model, and you just train that all jointly. And you get a captioner, image captioner. Lots of questions. OK, go ahead.
Are these 300-dimensional embeddings dependent on the images used, or are they generated independently?
Yeah, so these 300-dimensional embeddings, they're just independent of the image. So every word has 300 numbers associated with it.
How is that generated?
So we're going to backpropagate into it. So you initialize it random, and then you can backpropagate into these vectors x, right? So those embeddings will shift around. They're just a parameter. Another way to think about it is it's, in fact, equivalent to having a one-hot representation for all the words, and then you have a giant W matrix where every single, you multiply W with that one-hot representation, and if that W has 300 output size, then it's effectively plucking out a single row of W, which ends up being your embedding. So it's kind of equivalent. So just think of it, if you don't like those embeddings, just think of it as a one-hot representation, and you can think of it that way. Go ahead.
Does the model learn to output the end token?
Yes, the model learns to output the end token.
What do you use to define the end token?
Yeah, so in the training data, the correct sequence that we expect from the RNN is the first word, second word, third word, end. So every single training example will sort of have the special end token in it. Go ahead.
In H1 and H2, are you again receiving the same output from the VGGNet, or are you passing in like a twice as big?
Yeah, thank you. So the question is like where, so in this example, we're only plugging in the image at the very first time step. We're not plugging it in the other time steps. You can wire this up differently, where you plug it into every single state. It turns out that that actually works worse. So it actually works better if you just plug it in the very first time step. And then the RNN has to juggle these both tasks. It has to remember about the image what it needs to remember through the RNN. And it also has to produce all these outputs. And somehow it wants to do that. There are some hand-wavy reasons I can give you after class for why that's true.
So when you train it, do you just have to basically be careful to only give it the concatenate output when you give it the start token, and then give it the subsequent tokens in the labels, and then the end token, and then the next image from the next concatenate?
I see.
You're kind of alternating inputs in that way?
Not quite. So at training time, a single instance will correspond to an image and a sequence of words. And so we would plug in those words here, and we would plug in that image, and we So at training time, you have all those words plugged in on the bottom, and you have the image plugged in, and then you unroll this graph, and you have your losses, and you backprop. And then you can do batches of images if you're careful. And so if you have batches of images, they sometimes have different length sequences in the training data. You have to be careful with that, because you have to say that, OK, I'm willing to process batches of up to 20 words, maybe. And then some of those sentences will be shorter and longer, and you need to, in your code, worry about that, because some sentences are longer than others. We have way too many questions. I have stuff to go ahead.
So when we are training, do we do the training of these two separately, or it is backpropagated back to the image?
Yeah, thank you. So we backpropagate everything completely jointly, end-to-end training. So you can pre-train with the ImageNet, and then you put those weights there, but then you just want to train everything jointly, and that's a big advantage, actually. Because we can figure out what features to look for in order to better describe the images at the end. Okay. So when you train this in practice, we train this on image sentence data sets. One of the more common ones is called Microsoft Cocoa. So just to give you an idea of what it looks like, it's roughly 100,000 images and 5 sentence descriptions for each image. These were obtained using Amazon Mechanical Turk. So you just ask people, please give us a sentence description for an image, and you record all of it, and then that's your data set. And so when you train this model, the kinds of results that you can expect, or roughly what is kind of like this. So this is RNN describing these images. So it says that this is a man in black shirt playing guitar, or a construction worker in orange safety vest working on the road, or 2 young girls are playing with Lego toy, or boy is doing backflip on a wakeboard. And of course, that's not a wakeboard, but it's close. There are also some very funny failure cases, which I also like to show. This is a young boy holding a baseball bat. This is a cat sitting on the couch with a remote control. That's a woman holding a teddy bear in front of a mirror. I'm pretty sure that the texture here probably is what made it think that it's a teddy bear. And the last one is a horse standing in the middle of a street, but there's a road. So there's no horse, obviously, so I'm not sure what happened there. So this is just the simplest kind of model that came out last year. There were many people who tried to work on top of these kinds of models and make them more complex. I'd just like to give you an idea of one model that is interesting, just to get an idea of how people play with this basic architecture. So this is a paper from last year where, if you noticed, in the current model, we only feed in the image a single time at the beginning. And one way you can play with this is that you can actually allow the recurrent neural network to look back to the image and reference parts of the image while it's describing the words. So as you're generating every single word, you allow the RNN to actually make a lookup back to the image and look for different features of what it might want to describe next. And you can actually do this in a fully trainable way. So the RNN not only creates these words, but also decides where to look next in the image. And so the way this works is not only does the RNN output your probability distribution of the next word in the sequence, but this COMNET gives you this volume. So say in this case, we forwarded the COMNET and got a 14 by 14 by 512 by 512 activation volume. And at every single time step, you don't just emit that distribution, but you also emit a 512-dimensional vector that is kind of like a lookup key of what you want to look for next in the image. And so actually, I don't think this is what they did in this particular paper, but this is one way you could wire something like this up. And so this vector is emitted from the RNN, just like it's just predicted using some weights. And then this vector can be dot producted with all these 14 by 14 locations. So we do all these dot products, and we achieve, or we compute basically a 14 by 14 compatibility map. And then we put a softmax on this. So basically, we normalize all of this so that it's all, you get this what we call an attention over the image. So it's a 14 by 14 probability map over what's interesting for the RNN right now in the image. And then we use this probability mask to do a weighted sum of these guys with this saliency. And so this RNN can basically emit these vectors of what it thinks is currently interesting for it. And it goes back, and you end up doing a weighted sum of different kinds of features that the LSTM wants to, or the RNN wants to look at this point in time. And so, for example, the RNN is generating stuff, and it might decide that, OK, I'd like to look for something object-like now. It emits a vector of 512 numbers of object-like stuff. It interacts with COMNETs, with the COMNET activation volume, and maybe some of the object-like regions of that COMNET, of that activation volume, like light up in the saliency map in this 14 by 14 array. And then you just end up basically focusing your attention on that part of the image through this interaction. And so you can basically just do lookups into the image while you're describing the sentence. And so this is something we refer to as soft attention, and we'll actually go into this in a few lectures. So we're going to cover things like this, where the RNN can actually have selective attention over its inputs as it's processing the input. And so that's so I just wanted to bring it up roughly now, just to give you a preview of what that looks like. OK. Now, if we want to make RNNs more complex, one of the ways we can do that is to stack them up in layers. So this gives you, more deep stuff usually works better. So the way we stack this up, one of the ways at least, you can stack recurrent neural networks, and there's many ways. But this is just one of them that people use in practice, is you can straight up just plug RNNs into each other. So the input for one RNN is the hidden vector of the hidden state vector of the previous RNN. So in this image, we have the time axis going horizontally, and then going upwards, we have different RNNs. And so in this particular image, there are 3 separate recurrent neural networks, each with their own set of weights. And these recurrent neural networks just feed into each other. Okay? And so this is all always trained jointly. There's no train first one, second, third one. It's all just a single computational graph that we backpropagate through. Now, this recurrence formula at the top, I've rewritten it slightly to make it more general. We're still doing the exact same thing as we did before. This is the same formula. We're taking a vector from below in depth and a vector from before in time. We're concatenating them and putting them through this W transformation and then squashing them with the 10H. So if you remember, if you are slightly confused about this, there was a WXH times X plus WHH times H. You can rewrite this as a concatenation of X and H multiplied by a single matrix. Right? So it's as if I stacked X and H into a single column vector. And then I have this W matrix where basically what ends up happening is that your WXH is the first part of this matrix, and WHH is the second part of your matrix. And so this kind of formula can be rewritten into a formula where you stack all your inputs and you have a single W transformation. So it's the same formula. Okay, so that's how we can stack these RNNs, and then they're now indexed by both time and by layer at which they occur. Now, one way we can also make these more complex is not just by stacking them, but by actually using a slightly better recurrence formula. So right now, so far, we've seen this very simple recurrence formula for the vanilla recurrent neural network. In practice, you will actually rarely ever use a formula like this. A basic recurrent network is very rarely used. Instead, you'll use what we call an LSTM, or long short-term memory. So this is basically used in all the papers now. So this is the formula you'd be using also in your projects if you were to use recurrent neural networks. What I'd like you to notice at this point is everything is exactly the same as with an RNN. It's just that the recurrence formula is a slightly more complex function. Okay? We're still taking the hidden vector from below in depth, like your input, and from before in time, the previous hidden state. We're concatenating them, putting them through a W transform. But now we have this more complexity in how we actually achieve the new hidden state at this point in time. So we're just being slightly more complex in how we combine the vector from below and before to actually perform the update of the hidden state. It's just a more complex formula. So we'll go into some of the details of exactly what motivates this formula and why it might be a better idea to actually use an LSTM instead of an RNN. Go ahead.
Why are we suddenly switching back sigmoids and 10H?
Yeah, you'll see sigmoids in 10H, and it makes sense, trust me. We'll go through it just right now. So if you look for LSTMs online, you can look for LSTM and you go on Wikipedia or you go to Google Images, you'll find diagrams like this, which is really not helping, I think, anyone. The first time I saw LSTMs, they really scared me. Like this one really scared me. I wasn't really sure what's going on. I understand LSTMs, and I still don't know what these two diagrams are. So OK, so I'm going to try to break down LSTM. It's kind of a tricky thing to put into a diagram. You really have to kind of step through it. So a lecture format is perfect for an LSTM. OK. So here we have the LSTM equations. And I'm going to first focus on the first part here on the top, where we take these two vectors from below and from before. So x and h. H is our previous hidden state, and x is the input. We map them through that transformation W. And now, if both x and h are of size n, so there's n numbers in them, we're going to end up producing 4n numbers, okay, through this W matrix, which is 4n by 2n. So we have these 4 n-dimensional vectors, I, F, O, and G. They're short for input, forget, output, and G. I'm not sure what that's short for. It's just G. And so the I, F, and O go through sigmoid gates, and G goes through a tanh gate. Now, the way this let's see. So the way this actually works, the LSTM, basically, the best way to think about it is, oh, one thing I forgot to mention, actually, in the previous slide is normally recurrent neural network just has this single H vector at every single time step. And LSTM actually has two vectors at every single time step, the hidden vector and this what we call C, the cell state vector. So at every single time step, we have both H and C in parallel. And the C vector here is shown in yellow. So we basically have two vectors at every single point in space here. And what LSTMs are doing is they're basically operating over this cell state. So depending on what's before you and below you, that is your context, you end up operating over the cell state with these I, F, and O, and G elements. And the way to think about it is, I'm going to go through a lot of this. OK, so basically the way to think about this is, think of I, F, and O as just binary, either 0 or 1. We want them to have an interpretation of a gate. Like, think of it as either zeros or ones. We, of course, make them later sigmoids because we want this to be differentiable so that we can backpropagate through everything. But just think of I, F, and O as just binary things that we're computing based on our context. And then what this formula is doing here, C, you can see that based on what these gates are and what G is, we're going to end up updating this C value. And in particular, this F is called the forget gate. That will be used to reset some of the cells to 0. So the cells are best thought of as counters. And these counters, basically, we can either reset them to 0 with this F interaction. This is an element-wise multiplication there. I think my laser pointer is running out of battery. That's unfortunate. So with this F interaction, if F is 0, then you can see that we'll zero out a cell. So we can reset a counter. And then we can also add to a counter. So we can add through this interaction I times G. And since I is between 0 and 1, and G is between negative 1 and 1, we're basically adding a number between negative 1 and 1 to every cell. So at every single time step, we have these counters in all the cells. We can reset these counters to 0 with the forget gate, or we can choose to add a number between -1 and 1 to every single cell. Okay, so that's how we perform the cell update. And then the hidden update ends up being a squashed cell, so 10h of c, squashed cell that is modulated by this output gate. So only some of the cell state ends up leaking into the hidden state as modulated by this vector O. So we only choose to reveal some of the cells into the hidden state in a learnable way there. So there are several things to kind of highlight here. One maybe most confusing part here is that we're adding a number between -1 and 1 with I times g here. But that's kind of confusing because if we only had a g there instead, then g is already between -1 and 1. So why do we need I times g? What is that actually giving us when all we want is to increment a c by a number between -1 and 1? And so that's kind of like a subtle part about an LSTM. I think one answer is that if you think about g, it's a function of, it's a linear function of your context. No one has laser pointer by any chance, right? Okay. Oh, man. Okay. So g is a function of your, g goes through a 10h. Okay. So g is a linear function of your previous context squashed by 10h. And so if we were adding just g instead of I times g, then that would be kind of like a very simple function. So by adding this I in there and having a multiplicative interaction, you're actually getting a more richer function that you can actually express in terms of what we're adding to our cell state as a function of the previous h's. And another way to think about this is that we're basically decoupling these two concepts of how much do we want to add to a cell state, which is g, and then do we want to add to a cell state, which is I. So I is like, do we actually want this operation to go through? And g is, what do we want to add? And by decoupling these two, that also maybe dynamically has some nice properties in terms of how this LSTM trains. But we just end up, that's like the LSTM formulas. And I'm going to actually go through this in more detail as well, but maybe I should go through it now. Okay. So think about this as cells flowing through. And now the first interaction here is the f dot c. So f is an output of a sigmoid of that. And so f is basically gating your cells with a multiplicative interaction. So if f is 0, you will shut off the cell and reset the counter. This I times g part is basically giving you is basically adding to the cell state. And then the cell state leaks into the hidden state, but it only leaks through a 10h, and then that gets gated by O. So the O vector can decide which parts of the cell state to actually reveal into the hidden cell. And then you'll notice that this hidden state not only goes to the next iteration of the LSTM, but it also actually flows up to higher layers, because this is the hidden state vector that we actually end up plugging into further LSTMs above us, or that goes into a prediction. And so when you unroll this, basically the way it looks like is kind of like this. Which now I have a confusing diagram of my own. That's, I guess, where we ended up with. But you get your input vectors from below. You have your hidden state from before. The x and h determine your gates, fi, g, and o. They're all n-dimensional vectors. And then they end up modulating how you operate over the cell state. And the cell state can, once you actually reset some counters and once you add numbers between -1 and 1 to your counters, the cell state leaks out, some of it leaks out in a learnable way, and then it can either go up to the prediction or it can go to the next iteration of the LSTM going forward. And so that's the, so this looks ugly. So we're going to, so basically the question that's probably on your mind is, why did we go through all of this? There's some, why does this look this particular way? I should like to note at this point that there are many variants to an LSTM, and I'll make this point by the end of the lecture. People play a lot with these equations, and we've kind of converged on this as being like a reasonable thing. But there's many little tweaks you can make to this that actually don't deteriorate your performance by a lot. You can remove some of those gates, like maybe the input gate and so on. You can, turns out that this 10h of c, that can be a c, and it works just fine normally. But with a 10h of c, it works slightly better sometimes, and I don't think we have very good reasons for why. And so yeah, so you end up with a bit of a monster, but I think it actually kind of makes sense in terms of just these counters that can be reset to 0, or you can add small numbers between -1 and 1 to them. And so it's kind of like a nice, it's actually relatively simple. Now, to understand exactly why this is much better than an RNN, we have to go to a slightly different picture to draw the distinction. So the recurrent neural network, it has some state vector, right? And you're operating over it, and you're completely transforming it through this recurrence formula. And so you end up changing your hidden state vector from time step to time step. You'll notice that the LSTM instead has these cell states flowing through. And what we're doing effectively is we're looking at the cells, and some of it leaks into the hidden state. Based on the hidden state, we're deciding how to operate over the cell. And if you ignore the forget gates, then we end up basically just tweaking the cell by additive interaction here. So, so there's some stuff that is a function of the cell state, and then whatever it is, we end up additively changing the cell state instead of just transforming it right away. So it's an additive instead of a transformative interaction or something like that. Now, this should actually remind you of something that we've already covered in the class. What does it remind you of? ResNets, right? Yeah. So in fact, like, this is basically the same thing as we saw with ResNets. So normally with a ComNet, we're transforming the representation. ResNet has these skip connections here. And you'll see that basically ResNets have this additive interaction. So we have this X here. Now we do some computation based on X, and then we have an additive interaction with X. And so that's the basic block of a ResNet, and that's in fact what happens with an LSTM as well. We have these additive interactions where here the X is basically your cell, and we go off, we do some function, and then we choose to add to this cell state. But the LSTMs, unlike ResNets, have also these forget gates that we're adding. And these forget gates can choose to shut off some parts of the signal as well. But otherwise, it looks very much like a ResNet. So I think it's kind of interesting that we're converging on very similar kind of looking architecture that works both in ComNets and in recurrent neural networks, where it seems like dynamically somehow it's much nicer to actually have these additive interactions that allow you to actually backpropagate much more effectively. So to that point, think about the backpropagation dynamics between an RNN and an LSTM. Especially in the LSTM, it's very clear that if I inject some gradient signal at some time steps here, so if I inject gradient signal at the end of this diagram, then these plus interactions are just like a gradient superhighway here, right? Like these gradients will just flow through all the addition interactions, right? Because addition distributes gradients equally. So if I plug in gradient at any point in time here, it's just going to flow all the way back. And then of course the gradient also flows through these Fs, and they end up contributing their own gradients into the gradient flow. But you'll never end up with what we refer to with RNNs, a problem called vanishing gradients, where these gradients just die off, go to zero as you backpropagate through. And I'll show you an example concretely of why this happens in a bit. So in an RNN, we have this vanishing gradient problem. I'll show you why that happens. In an LSTM, because of this superhighway of just additions, these gradients at every single time step that we inject into the LSTM from above just flow through the cells, and your gradients don't end up vanishing. At this point, maybe I could take some questions. Are there any questions about what's confusing here about LSTM? And then after that, I'll go into why RNNs have vanishing gradients problem. Go ahead.
Why do we want O? Since we can
Yeah, so this O, you're asking about the O vector. Is that important? Turns out that I think that one specifically is not super important. So there's a paper I'm going to show you. It's called an LSTM search space odyssey. They really played with this. Take stuff out, put stuff in. There's also like these peephole connections you can add. So this cell state here, that can be actually put in with the hidden state vector as an input. So people really play with this architecture, and they've tried lots of iterations of exactly these equations. And what you end up with is almost everything works about equal. Some of it works slightly worse sometimes. So it's very kind of confusing in this way. I'll also show you a paper where they treated these update equations as just, they built trees over the update equations, and then they did this like random mutation stuff, and they tried all kinds of different graphs and updates you can have. And most of them work about, some of them break, and some of them work about the same. But nothing like really does much better than an LSTM. Any other questions? What else? Let's go into why recurrent neural networks have terrible backward flow. I'll show you a cute video also. So this is showing the vanishing gradients problem in recurrent neural networks with respect to LSTMs. So what we're showing here is we're looking at, we're unrolling a recurrent neural network over many periods, many time steps, and then we're injecting gradient and at say 128th time step. And we're backpropagating the gradient through the network. And we're looking at what is the gradient for, I think, the input to hidden matrix, one of the weight matrices, at every single time step. So remember that to actually get the full update through the batch, we actually end up adding all those gradients here. And so what's what's being shown here is that as you backprop, we've only injected gradient at 1/28th time steps, and we do backprop back through time, and this is showing the slices of that backpropagation. And what you're seeing is that the LSTM gives you lots of gradients throughout this backpropagation. So there's lots of information that is flowing through. And this RNN just instantly dies off. That just the gradient, we say, vanishes. It just becomes tiny numbers. There's no gradient. So in this case, I think it decays in about 8 time steps or so, like 10 time steps. And so all this gradient information that we've injected did not flow through the network. And you can't learn very long dependencies because all the correlation structure has been just died down. And so we'll see why this happens dynamically in a bit. There's some comments here which are also funny. This is like YouTube or something again. Okay, anyways. Okay, so let's look at a very simple example here where we have a recurrent neural network that I'm going to unroll for you. In this recurrent neural network, I'm not showing any inputs. We only have hidden state updates. So here I'm initializing a weight WHH, which is the hidden state, hidden to hidden interaction. And then I'm going to basically forward a recurrent neural network. This is a vanilla recurrent net for some t time steps. Here I'm using t50. So what I'm doing is WHH times the previous hidden time step and then ReLU on top of that. So this is just a forward pass for an RNN, ignoring any input vectors coming in. It's just WHH times H, threshold, WHH times H, threshold, and so on. So that's the forward pass. And then I'm going to do backward pass here, where I'm injecting a random gradient here at the last time step. So at the 50th time step, I inject some gradient, which is random. And then I go backwards and I backprop. So when you backprop through this, right, you have to backprop through a ReLU. Here I'm using a ReLU. You have to backprop through the WHH multiply, then through ReLU, WHH multiply, and so on. And so the thing to note here is, so here I'm undoing the ReLU. Here's where I'm backpropagating through the ReLU. I'm just thresholding anything that where the inputs were less than 0. And here I am backpropping the WHH times H operation, where we actually multiply by the WHH matrix before we do the nonlinearity. And so there's something very funky going on when you actually look at what happens to these DHS, which is the gradient on the H's, as you go backwards through time. It has a very kind of funny structure that is very worrying. As you look at like how this gets chained up in the loop, like what are we doing here with these 2 time steps?
Potentially taking the dot product of all zeros?
Taking the dot product of all zeros. Yeah, so I think at some time steps maybe the outputs, the ReLUs were all dead, and so you may have killed it. But that's not really the issue. The more worrying issue is, well, that would be an issue as well. But I think one worrying issue that people definitely spot as well is you'll see that we're multiplying by this WHH matrix over and over and over again. Because in the forward pass, we multiply by WHH at every single iteration. When we backpropagate through all the hidden states, we end up backpropagating this formula WHH times HS. And the backprop turns out to actually be that you take your gradient signal and you multiply it by the WHH matrix. And so we end up multiplying by WHH. The gradient gets multiplied by WHH, then thresholded, then multiplied by WHH, thresholded. And so we end up multiplying by this matrix WHH 50 times. And so the issue with this is that the gradient signal basically, okay, 2 things can happen. Like if you think about working with scalar value, suppose that these were scalars, not matrices. If I take a number that's random, and then I have a second number, and I keep multiplying the first number by the second number, so again and again and again, what does that sequence go to? So there's 2 cases, right? If I keep multiplying with the same number, either I die or it just goes complete. Yeah, so if your second number was exactly 1, yeah? So that's the only case where you don't actually explode. But otherwise, really bad things are happening. Either we die or we explode. And here we have matrices. We don't have a single number. But in fact, it's the same thing happens. The generalization of it happens. If the spectral radius of this WHH matrix is, which is the largest eigenvalue of that matrix, if it's greater than 1, then this gradient signal will explode. If it's lower than 1, then the gradient signal will completely die. And so basically, since the RNN has this very weird, because of this recurrence formula, we end up with this very just terrible dynamics, and it's very unstable, and it just dies or explodes. And so in practice, the way this was handled was We can control the exploding gradient. One simple hack is if your gradient is exploding, you clip it. So people actually do this in practice. It's like a very patchy solution. But if your gradient is above 5 in norm, then you clamp it to 5 element-wise or something like that. So you can do that. It's called gradient clipping. That's how you address the exploding gradient problem. And then your recurrent nets don't explode anymore. But the gradients can still vanish in a recurrent neural network. And LSTM is very good with the vanishing gradient problem because of these highways of cells that are only changed with additive interactions where the gradients just flow. They never die down because you're multiplying by the same matrix again and again or something like that. So that's roughly why these are just better dynamically. So we always use LSTMs, and we do gradient clipping usually. So because the gradients in an LSTM can potentially explode still. But they don't usually vanish. Go ahead.
Just like you used ReLU in this RNN, do people use ReLU in LSTMs? And if they have, like, what were the results?
Thank you. So here I'm using ReLU. People sometimes use 10H in Veillon recurrent neural networks as well. For LSTMs, it's not clear where you would plug in. It's not clear in this equation, like exactly how you would plug in a ReLU and where. Maybe instead of maybe for G, I'm not sure. So instead of 10H, we would use G here, ReLU. But then, so these cells would only grow in a single direction, right? So maybe then you can't actually end up making it smaller. So that's not a great idea, I suppose. Yeah. So it's basically, there's no clear way to plug in the ReLU here. So yeah. One thing I'll note is that in terms of these superhighways of gradients, this viewpoint actually breaks down when you have forget gates. Because when you have forget gates, where we can forget some of these f's with a multiplicative interaction, then whenever a forget gate turns on and it kills the gradient, then of course the backward flow will stop. So these superhighways are only kind of true if you don't have any forget gates. But if you have a forget gate there, then it can kill the gradient. And so in practice, when we play with LSTMs, or we use LSTMs, I suppose, sometimes people, when they initialize the forget gate, they initialize it with a positive bias, because that biases the forget gate to turn on, to be always kind of turned off, I suppose, in the beginning. So in the beginning, the gradients flow very well, and then the LSTM can learn how to shut them off if it wants to later on. So people play with that bias on that forget gate sometimes. And so the last slide here, I wanted to mention that LSTMs, many people have basically played with this quite a bit. So there's a Search Space Odyssey paper where they try various changes to the architecture. There's a paper here that tries to do this search over a huge number of potential changes to the LSTM equations. And they did a large search, and they didn't find anything that worked substantially better than just an LSTM. So, yeah. And then there's this GRU, which also is relatively actually popular, and I would actually recommend that you might want to use this. A GRU is a change on an LSTM. It also has these additive interactions, but what's nice about it is that it's a shorter, smaller formula, and it only has the single H vector. It doesn't have an H and a C. It only has an H. So implementation-wise, it's just nicer to remember just a single hidden state vector in your forward pass, not 2 vectors. And so it's just a smaller, simpler thing that seems to have most of the benefits of an LSTM. So it's called GRU. And it almost always works about equal with LSTM in my experience. And so you might want to use it, or you can use an LSTM. They both kind of do about the same. And so summary is that RNNs are very nice, but the raw RNN does not actually work very well. So use LSTMs or GRUs instead. What's nice about them is that we're having these additive interactions that allow gradients to flow much better, and you don't get a vanishing gradient problem. We still have to worry a bit about the exploding gradient problem, so it's common to see people clip these gradients sometimes. And I would say that better, simpler architectures are really trying to understand how come, like there's something deeper going on with the connection between ResNets and LSTMs, and there's something deeper about these additive interactions that I think we're not fully understanding yet, and exactly why that works so well, and which parts of it work well. And so I think we need much better understanding, both theoretical and empirical in the space, and it's a very wide open area of research. And so, yeah. So it's 4:10. That's the end of the class, right?
LSTM, is there any gradient exposure?
With an LSTM, people still clip gradients. They can, I suppose, still explode. So it's not as clear why they would, but you keep injecting gradient into the cell state, and so maybe that gradient can sometimes get larger. So it's common to clip them, but I think not as maybe important maybe as an RNN. I'm not 100% sure about that point. Good?
Is there a neurological basis for LSTMs?
neurological basis. I have no idea. It's interesting. Yeah. Okay, I think we should end the class here, but I'm happy to take more questions here.